Hello everyone, this is Enis from BeeMagnetics. Today I will present to you another system-level optimization tool of BeeMagnetics Engine, which is the system-level flyback design. We first define the core boundaries of our design. You can fix the input voltage requirements of your converter, or you can define it as an interval. Let's try it with a 65 watts 20 volt flyback converter, which is very common in the industry. Then, more importantly, we define our design priorities. By adjusting these weight percentages for volume, efficiency and cost, we directly steer the optimization algorithm to match our specific project goals. We can also define our operating environment and winding layout preferences. For now, let's say sandwich PSP method is okay for our design. Moving down to the design space, instead of fixed values, we set up sweeps for switching frequency, current ripple factor and turns ratio. This allows the software to explore a massive matrix of possibilities to find the true optimum points. As usual, we get used to define current ripple factor 30 or 40%. However, the real optimum design may be missed due to these predefined factors. Therefore, we have to sweep and leave the decision to powerful BeeMagnetics Engine. Next, we move to the component selection. For the primary switch, I'm adding 650 volts to 700 volt series FETs from 3 different vendors. This approach allows our engine to evaluate and compare different products that meet our specific technical requirements. If you do not want to filter them by hand, just select everything together and leave all calculations to BeeMagnetics Engine. That's also a good choice. Let's have a look at the diodes. You have the flexibility to do the exact opposite. If you wish, you can easily select all available products from just a single vendor too. And moving to caps, we can quickly narrow down our candidate pool based on parameters like rated voltage. Here, as you can see, we can directly select some certain voltage levels for the caps too. When it comes to the transformer database, we can systematically filter our choices. We can start by selecting core geometry and then drill down into specific core sizes or specific materials. However, here is the best part. You don't actually have to filter anything at all. You can just define your system requirements, include the entire database and let the software do the heavy lifting. As you can see, estimated runtime for this comprehensive sweep is just about a few seconds, so go ahead, grab a cup of coffee and when you are back, you can dive right into the results. And just after a few seconds, our optimization is already completed. We kick off our results screen with the generated design space. Here on the left, you can clearly see the crucial trade-off map between the snubber loss and leakage inductance for the simulated candidate designs. Right below it, we have the precise schematic of our designed flyback converter too. Scrolling down to the summary section, we get a crystal clear high-level overview. The engine provides a complete breakdown of our system metrics in terms of total loss, total volume and total cost. It's all right here as a comprehensive summary. But as we are engineers, we would like to see more and more details. If you notice these magnifier buttons next to the selected components, you already understood that you have to click on them. And let's start with the primary FETs as per. On this screen, we see the exact MOSFET chosen by the algorithm, its current market price, and its worst-case scenario loss within our input voltage range. We provide a detailed radar chart illustrating the exact loss distribution too. To ensure safe operation under these conditions, the engine recommends a specific heatsink and calculates the maximum operating junction temperature for you. Moving over the secondary side diode, you are greeted by a similar comprehensive structure. Another heatsink is selected for that diode. If the algorithm decides not to use any heatsink, if it found that design secure from thermal point of view, then it will leave as an empty space. Now, let's dive into what makes this engine exceptionally powerful, which is our magnetic design details. Here in the transformer analysis step, we get a neat summary of our winding type, turns ratio, wire values, and specific core manufacturer complete with the part number and price. For simplicity, core and copper losses are cleanly visualized in a bar chart form. You'll notice that the engine successfully kept the leakage inductance close to the 1%, strictly respecting the boundaries to prioritize. As we scroll down, you will encounter 4 unique visualizations driven by the geometric validation and finite element method engines. First, our structural winding layout visually guarantees that your calculated turns and insulation materials will actually fit perfectly within the core's window area in the real world. And then you can see the results of finite element solutions. And we didn't forget the protection circuitry too. The RCD snubber we selected during input has been custom designed specifically for this transformer. The model even displays the maximum voltage stress your MOSFET will face, ensuring entirely safe clamping. Finally, with a single click on the Print Report button at the top, you can export all of these accurate and clear design details, FEM visuals, and loss breakdowns into a single PDF. So instead of losing days on optimization, you can go straight into prototyping right now, before that coffee you just filled up even gets cold. Thanks for watching and see you on our next video.